Alright, so now is the big video. We're going to be talking about the SVD. So let's go ahead and start. So let A be an m by n matrix. Oops, not square. My headphones keep coming off. Oh, let's see if I can keep them on my head. So let A be an m by n matrix. Then 1. A transpose A is n by n and symmetric, right? Therefore, A transpose A is orthogonally diagonalizable, and we can write A transpose A as V d V transpose, right? Where V is an n by n and orthonormal, right? And D is diagonal with eigenvalues along the diagonal. It's n by n diagonal with eigenvalues along the diagonal. Good. And by the way, that's true from the spectral theorem. Good. A transpose is m by m and symmetric. You can prove that, I think, fairly easily. Write the symmetry, because if you take the transpose of the product, it's the product of the transposes in reverse order. So you end up with taking, yeah, if you look at, this is just a little side note, if you take A transpose, right, that's A transpose times A transpose. Is that right? No, A. What did I just do? A transpose is A transpose times, yes, A transpose. There we go. A transpose. There we go. Good. Okay, so A transpose, or A transpose, is symmetric as well. And so therefore by the, what theorem? The spectral theorem, we can write A transpose as U times D2, maybe I'll call this D1 for now, U transpose. And again, that's just an eigenvector eigenvalue decomposition, where U again, oops, there are different sizes, right? U is m by m and orthonormal, and D2 is m by m and diagonal with evals on the diagonal, right? Good. All right. I wonder, so we can show, I don't want to give it away because I think it's one of the first exercises, we can show that if lambda is a non-zero eval of A transpose A, then lambda is an eval of A transpose. And so what am I saying here? I'm saying that the non-zero, let me go ahead and write the conclusion here. The non-zero diagonal entries of D1 are equal to the non-zero diagonal entries of D2. So this is, it's kind of weird, but just take a look at this for a second. This D1 right here is n by n, D2 is m by m, and what we're saying is they have the same number of non-zero eigenvalues. Therefore, what ends up happening if m is not equal to n, right, is that you end up just zero padding for the rest. So, you know, for example, just as a quick numerical example, D1 might be equal to, let's see if I can write this nicer. D1 might be something like 3, 0, 0, 2. And then D2 might be something like, so the 3 and the 2 have to be there because those are identical. But then after that, we could have, you know, any number of zeros in here. So this is what I meant by the zero padding. You know, you could just keep running zeros. And so in this case, right, you would have 2 0 eigenvalues and then the 3 and the 2. Good. So that's what we mean by the non-zero diagonal entries of D1 are equal to the non-zero diagonal entries of D2. Very good. Okay. So what we're getting at is the following definition now. Definition. The singular value, or a singular value for matrix A is defined to be sigma I, which is the square root of lambda I, where lambda I is an eigenvalue of either A transpose or A transpose A. It doesn't matter, right? Because they're either equal to each other or it's 0. Good. And so these are the singular values. The singular values, the sigma I, are the square root of the eigenvalues. Now, I just wrote down here that I'm taking the square root of an eigenvalue. What does that suggest? That suggests that the eigenvalues are probably going to be greater than 0, greater than or equal to 0. And so we get that sigma I is real. And so there's another exercise. Show that lambda I is greater than or equal to 0 if it's an eigenvalue of A transpose or A transpose A. And there's a little hint there too. Okay, so I've now defined 3 things, right? I've defined the sigma I's, I've defined the matrix U, and I've defined the matrix V. Okay, and so now I'm ready to put together the singular value decomposition theorem. Thus, let A be any m by n matrix. The singular value decomposition is a matrix factorization, or SVD. SVD, sorry about that, my writing's not very good, is given by U sigma V transpose, where U is m by m and orthonormal, and guess what? It's from the eval or evex of A transpose. V is n by n and orthonormal, and those are from the evex of A transpose A. And sigma, what is sigma? What's the shape of sigma? It has to be m by n and diagonal with sigma I along the diagonal. Good. And this is the SVD. And what's so important about the SVD? The key thing about the SVD is that this factorization, unlike eigenvectors and eigenvalues, this factorization can be performed on any matrix A. Okay, therefore, I don't have to be careful about A being defective or getting complex eigenvalues or anything like that. If I can just take any m by n matrix, I can formulate the SVD. I can factorize it this way, or factor it this way. Good. Okay, and now there's really a key feature about these three matrices as well. And what's going to happen is I'll just let you in on the secret. The columns of U, oops. So if matrix A has rank K, then the U1 through UK forms an orthonormal basis for the column space of A. Wow. Secondly, V1 through VK forms an orthonormal basis for the row space of A. And so right off the bat, remember the four subspaces. If I can find this singular value decomposition of the matrix A, then I have found an explicit description of all four fundamental subspaces. Okay, because if this is the row space of A, right, then what can you say about the null space of A? It's spanned by, or it has an orthonormal basis of Vk plus 1 up to Vn, right, is an orthonormal basis for the null space of A. Is the null space important when you're solving Ax equal B? Oh yes, it's very important. Because you need the null space, in fact you need a basis for the null space when you're solving Ax equal B, because it comes into play when you have an infinite number of solutions, right? So if the null space is anything but just the zero vector, you're going to have an infinite number of solutions, and so you can describe those solutions in full if you have a basis for the null space of A. Good. And of course, a basis for the column space is very important too, because once you have that, let's just talk about it in words a little bit. If I have a basis for the column space of A and a vector B, for example, is not in the column space, then I'm able to form an orthogonal projection of B. I have to draw a picture, I just can't say it. So if this is my vector B, and this is the column space of A, and this is the null space of A transpose, right, then if I have a orthonormal basis for the column space of A, I can formulate the projection matrix to take B into B hat, which is the projection into the column space, and now I can solve Ax hat equals B hat, and this is the least squares solution. Okay, I probably said too much. I got excited there at the end. I better stop here. Okay, I'll come back down to the ground in our next video. See you then.